Hello everyone, welcome to our video series on the architecture of business applications. We want to cover various things we've learned over the last several years. I founded this company called Remigis Technologies more than 2 decades ago, and all this time we have been building challenging large business applications for enterprise customers in the banking, finance, capital market space, government clients, etc. We have learned a lot about software architecture and their peculiarities, challenges in this period. So I thought it will be great if we cover some of these in the video series that we want to create. So let's get started. So first, what this series will cover and won't cover. Okay, we will not be covering front-end software. We will not be talking about the architecture of mobile apps, for instance. We'll only be talking about server-side architecture, because that's where we find architecture to be interesting and challenging, and it has all sorts of trade-offs and shades of gray and so on. So we will only be talking about server-side code. We will not be talking about programming languages. We will not be talking about these components which are used in the architecture of a large business application. We will not be talking, for instance, about whether RabbitMQ is good or Kafka is bad, or is the Kong API gateway the best API gateway, and so on and so forth. We are not going to compare products. And we will not be talking about cool architectural features or services of these public clouds like AWS and Azure. Okay, so those things are not to be covered. The stuff that we will be covering server-side software architecture. We will be taking a look at these typical classical terms with which architecture is discussed. Things like service-oriented architecture and things like that. What do those things mean? And we will be taking a kind of a deep dive into you can say the practice of architecture. How do we go about, quote unquote, doing architecture? Building a software application, implementing functional features is one side, and the architecture is everything else. So how do we do architecture in a kind of logical and systematic way? So that would be the meat of what we will be covering. Okay, how architecture is seen conventionally. Okay, when we look at architecture, when people talk about architecture, they throw around certain terms, and these become very standard, and they have sort of gained wide acceptance without being very well defined. So let's look at these terms. The first architectural concept is a monolithic architecture, a single mass of software. Now we will see that there are shades in that, but monolithic is one common term. The other term is the next idea is these n-layered architectures, 3-layer architecture, 2-layer architecture, and so on. Front end, back end, 2 layers. Application server, transaction server, database server, 3 layers, etc., etc. So that is one common term. The third term that we hear often, which is quite orthogonal to all these layers, is the service-oriented architecture. So what's a service-oriented architecture? What is a service? Then we have event-driven architectures. An event-driven architecture is an architecture where events happen, like messages come in and triggers are fed into the system, and the system reacts to it. So what the hell is that? Then we have microservices architecture. So all of these are interesting terms. This is a very conventional way of looking at architecture. Now, when you talk to people, you usually find people using these terms with great confidence, but we don't get the feeling that this alone is good enough. A discussion on architecture has to be much more nuanced. So, in practice, serious work in the area of software architecture needs to be much more nuanced, needs to have a blend of many ideas, etc., etc. So, the entire idea of how we look at architecture needs to be re-looked at from the ground up. Okay, so that's going to be sort of one of the things which I'm looking forward to doing in this series. I have this tendency to get into fundamentals and make sure my thoughts are clear, at least clear enough for me. So, the next question that I want to look at is, why do we need architecture? Now, why is it that we want to talk about this subject of architecture at all? When it's almost as if, on the one hand, we have these very trendy buzzwords like service-oriented architecture, microservices architecture. On the other hand, if you ask a person what is the foundation on which you want to start building your architecture concepts or your architecture design, there is non-clarity. So, why do we need architecture at all? So, if we want to understand this, we need to look at what would be the architecture of your software if nobody deliberately did any architecture specification. What would it land up being? So, that would be what I call a college student architecture. If a college student has learned Java and has then learned a little bit of how to build web applications, he'll be writing applications in Java and he'll be creating a jar file, and then he will be deploying it on his laptop and testing it out, and that would be something, right? That would be a working application. Now, if we have to understand why we need to do architecture, we need to understand what he does and what more do we need to do. If we don't understand that, we don't have a takeoff point without that. So, let's look at what architecture emerges by default when this Mr. College student or Miss College student builds his Java application. So, he will have one server, which could be his laptop to begin with, one server with one disk, and on that server there will be one database. Everybody uses some database or the other for the conventional business applications. One database, one Tomcat. We are talking about Java, right? So, we will talk about Tomcat as a typical application engine. So, all the code will be in one jar file and he will plug it into his Tomcat and get things going. So, things will work on his laptop like that. And one IP address for the server. So, the server will have an IP address and there will be one internet link. As in, if he wants to make his application accessible from the outside, this laptop will have to have an internet connection. So, this is the stack. One computer, we call it a server, one computer with a hard disk, one database, one Tomcat, one bundle of Java code implementing his web service calls, and one IP address. The entire study of architecture starts from one question: why isn't this enough? Why isn't the college student's default software architecture enough? If it is enough, then we can close this entire story and get on with building applications. There is no need for designing the architecture of your application if the default architecture serves all purposes. Okay, so this is the core idea. The answer to this question, why isn't this enough? The answer to this question comes from NFR, non-functional requirements. Now, to be able to understand what this is, we need to understand functional features versus NFR. So, everything functional is functional and the rest is non-functional, and non-functional requirements are the seed from which all the architecture challenges come up. So, to be able to understand all this, we need to understand what is functional requirements. Look at any business application, look at any application. Let us say a simple application where you are using the application to maintain accounts for your business. So you have a screen to enter vouchers, you have another screen where you'll see all the vouchers entered by other people. You will have a screen where income and expense entries are offset against each other, and you'll get maybe something called a trial balance, etc. Now all of these things are things you need to do with the software. Functional things. So these are the functional requirements of any business application. If you have some other application which, let us say, controls machines in a factory, so those will be the functional requirements of that software. It will turn on a machine, it will monitor the speed of the machine, it will switch off machine number 1 when machine number 2 is ready. Those are the functional features of that software. So every software has functional features. But in order for the software to be useful in large and challenging real life scenarios, which means not the college student scenario, in a real life scenario where there are many demanding, many demanding demands on the software needs to fulfill non-functional requirements too. This is the critical differentiation. So we will look at non-functional requirements. For instance, one of the commonest non-functional requirements is the throughput. What is throughput? Throughput is a technical term which we are all familiar with in our industry. It talks about the rate at which transactions, let us say, hit the system. So if the software is being used to record transactions, purchase transactions, then what is the rate at which the software needs to operate? That is its throughput. So if I have a throughput requirement for my software, let us say I have a requirement of 3000 transactions per hour. That is one kind of requirement. 20,000 transactions per second, that's a very different number. 3000 per hour is less than 1 per second. 20,000 per second is a phenomenal figure. So this is a non-functional requirement. Transactions will be handled by the software, whether it is 1 per minute or 1 per hour or 1 per second or 20,000 per second. So the rate at which the software needs to handle transactions is a non-functional requirement. The fact that it needs to record transactions is a functional requirement. Do you see the difference? So non-functional requirements are of various kinds. Let's just go through some more of these. Okay, what are the other typical non-functional requirements? Because this is where architecture comes up. The practice of architecture is born out of an appreciation of non-functional requirements. If there were no, as I keep saying, if there were no difficult non-functional requirements, college student architecture would be adequate. One laptop would be enough. So let's look at what are the cool non-function requirements that large enterprises throw at us with respect to their business applications. The second non-functional requirement example, NFR example, is peakiness of the load. Peakiness is a word we use which means does the load figure peak, as in does it show a sharp rise during a short period of time? So the opposite of peakiness is flatness. So if the software which we are trying to build or trying to run will experience load which is uniform for like 12 hours a day or 24 hours a day, that is a very non-peaky load. But real life business applications often show terrible peakiness. For instance, a trading exchange may say that they are handling several 100 million trades per day, which is cool in itself, quite impressive. But the peakiness takes it into a completely different level of craziness. They may say that 50% of the day's transactions are handled in the first 15 minutes and the last 15 minutes of the trading day. That's peaky for you. That's crazy peaky. So you can have peakiness in a daily cycle, you can have peakiness in a monthly cycle, a yearly cycle. I'll give you some very popular examples of peakiness in load. We all know that the Indian government runs a portal where we can file income tax returns. But how many returns are filed, do you think, during a typical day? So for most part of the year, the figure is 0. Nobody is filing income tax returns every day. Income tax returns are filed at the end of the financial year. And there, I am told that once the financial year ends, in India it is 31st March, so the 1st April onwards, we are theoretically in a position to file our income tax returns. Nobody files income tax returns on the 1st of April. Nobody is filing anything at that time. They are filing returns only in the last 3 days before the deadline hits. And there may be very good reasons for this. We are not getting into that. But my point is, the entire country's annual income tax returns are filed in 3 days. That's peakiness for you. Another example which is very common in the retail commerce sector in India is the Diwali dhamaka. The Diwali freak out festive season probably accounts for, I don't know, 30% of the year's retail sales. I think in the US you have, what do they call it? Black Friday or some such thing before Christmas somewhere, or before Thanksgiving. There is some crazy period of absolutely berserk retail sales in a very short span of maybe a week or 5 days or something like that. So there are discounts from the suppliers, and there are huge expressions of demand from the market. So that's peaky load for you. Now all this stresses out your software system. The third thing that hits software systems, which are a common NFR in the systems we build, are latencies. Latency refers to the time delay from the start of an operation to the end. For instance, if I want to see what are the available railway tickets before I can book a ticket, I should be able to type in my query and hit enter and see the results in, let us say, 3 seconds. So that's a 3-second latency limit. The team which is building the software knows that the customer, which may be the railway booking department, will refuse to accept the software if the software takes, say, 10 seconds to show this list. So that's a latency requirement, which is an NFR. So if you understand this, the expectation that you will show the available seats in the train, that is a functional requirement. You will show the available berths. The expectation that you will show that data in 3 seconds is a non-functional requirement. That's not functional in the language of software. Then there are NFRs regarding speed of specific subcategories of calls. For instance, there could be there could be certain calls which are triggered extremely frequently. There could be certain operations which need to happen within a certain amount of time, or which need to show data which is very current. For instance, a very common example, again in the world of banking transactions and so on. A shopkeeper bills my credit card and he doesn't trust his systems. He wants to see the last 10 transactions which his bank is showing against the credit card which he has, against all the credit cards which he is billing. So if he bills my credit card, he wants to see that amount showing up in his last 10 transactions. So he'll bill my credit card, and within 5 seconds he will go to the next screen and he will check the last 10 transactions, which means that the software has to accept my credit card payment and insert it into the transaction statement screen in a matter of 3 seconds. So there is a speed expectation here which can be very demanding sometimes. The next NFR, very common, is the data size. Are you handling like 10 gigabytes of data or 10 terabytes or 100 terabytes? The entire architecture changes if the data volume goes up by, say, 100x. The next common NFR is to do with data flow. How fast does data need to flow? Common example. If I need to replicate data from one data center to another, and I can do it every 6 hours, and it takes 10 minutes to do the replication, then that's a very easy NFR. If I need to do this every night and the data is in terabytes and it takes 12 hours to replicate, then we have an NFR challenge. That NFR is very hard to meet. So the rate at which data needs to flow from one place to another can change things very sharply. It can change your architecture a lot. The next NFR is very common in the enterprise, financial sector, etc., etc. Uptime. How long can the system be down? Can the system be down 1% of the time? This means that the system can be down for 3.5 days every year. Can you imagine any banking system which will give you only, the rest of the year available on the system, and it will be shut down for 3 days in the year? No net banking system in the world will accept this as an acceptable level of performance. So there is an uptime expectation. That's an NFR. So 99% uptime is useless for net banking systems. They need to at least do 4 nines or 5 nines, which is 99.99% of the time. So uptime and availability expectations are a very common NFR. The next one is to do with access patterns. I need to be able to access this data, but only from here and not from there. For instance, I am a manager. I should be able to access very critical confidential reports on the system, but I should be able to access that report only from the desktops in the office. If I log into the system from outside the office, I should not be allowed to access that data. So these are access restrictions. The data is the same. The report will contain the same data, but it will be accessible to me under certain conditions, from certain places, maybe during certain times of the day, etc., etc. So, that's an NFR. Then you have compliance expectations. Many countries have begun to talk about data residency laws. You build a banking system, the data related to the transactions of the citizens of my country must reside on servers in my country alone. You want to operate in 10 countries, you better figure out how that country's transaction data sits physically in servers in that country. My country's transaction data sits physically in servers in my country. That's a very common legal and compliance expectation which is coming up in many parts of the world today. Now, the moment you have data residency restrictions, you have to comply with them, and if you have to comply with them, the architecture changes. So this is another NFR. There are many other compliance related NFRs which happen. We'll not get into too many lists, but this is a very good survey of the flavor of the NFRs which hit the design and the architecture of a business application. The architecture of a software service is best designed by starting with the NFRs. First, check whether the college student architecture will do the job or not. So how do we check this? Look at the NFRs and see what throughput you get on a single server. For instance, if the expectation is that we will need to handle only 1 million transactions a day, that's a very small number for modern computers. 1 million a second is huge, 1 million a day is quite small. So if we need to handle only 1 million transactions a day, and during peak loads there will be 2000 transactions per second, not more than that. Now, if that is the NFR given to you, then the architecture has to handle 2000 transactions per second. This can be handled by one server comfortably. Modern servers will often not, even break a sweat to handle a few thousand transactions per second. So your architecture is simple. If your throughput requirements are much higher, the architecture changes. Then look at the data volumes. Will you be expected to handle very large data volumes? If you do, then the architecture has to reflect that. What about rate of data flow? Does data need to flow from one machine to another very fast? Availability. Now, availability is, again, as I was saying, we're talking about downtime and uptime here. When we talk about availability, availability can be at various levels, okay? When we talk about a large software application, we need to look at how failures in the system will impact the availability of the software. So, you have to segment it separately into various angles and look at the availability from different angles. The first angle is, how will the software be available if one server fails? Typically, whenever there is a real life application, the availability requirements for that application will not allow you to use one server. Almost any application will have an availability expectation, which will say, oh, you can be down for not more than 15 minutes at a time, or 5 minutes at a time, or 30 seconds, or whatever. But even 15 minutes, even half an hour of downtime is impossible to handle with one server. Like, if I have one server and I don't have a second server, then I have to repair that server. So it can take me anywhere between a few hours to a few days, right? So that impacts architecture. The second issue will be availability in the case of failure of storage. What happens if a disk fails? Then the third challenge will be, what happens if the network goes down? My server is okay, my disks are fine, but I can't connect to the server, I can't connect to the software because networks are down. So what do I need to do in case I need to take care of one network link failure? Access patterns. Will I be able to handle all the access pattern expectations by just having everything running on one computer? Will I need to separate out different parts of the data, different parts of the services into different systems in order to meet the expectations about access patterns? So from all these explorations will emerge finally a picture which will give you a foundation to build the architecture of your business application. So business application architecture is built on a foundation of NFR. Some basic points about architecture. We have sort of surveyed things. Now I'm sort of putting some of these things together. First point, very obvious, architecture is a non-issue. The college student architecture will work if NFRs are simple and easy. If the NFRs cannot be met with the college student architecture, then you need to start looking at things piece by piece. The next point to understand is architecture is application specific. One application will require one architecture, another application may require a very different architecture. So there is often a tendency to generalize, a tendency to say, oh, we prefer architecture type X. That doesn't work. That simply means that you are insensitive to what the application requires. So architecture is application specific. Architecture is also hardware specific. You know, the kind of hardware you are going to run your system on will often strongly influence the architecture of the system. To give you an extreme example, which is not very common these days, if I know that I have to build my application to run on IBM Z series mainframes versus if I know that I have to build the application to run on, you know, x86 family of Intel or Intelish family, Intel compatible family of servers, the architecture will be very different. With Z series mainframes, I'll have 1 or 2 mainframes at the most handling the whole load. With Intel servers, I can go into clusters of servers. That's a completely different architecture. So architecture is very hardware specific. Architecture is also software stack specific, which means, am I, building the am I building like the application on a data store which is inherently distributed? Am I building the application in such a way that it will, all transactions will hit a single database running on a single system? So software stack also changes the architecture. The architecture which is natural when I am building using PHP may not be the best architecture when I'm developing my application in Java or in Go. So the architecture is software stack specific. Architecture also changes when boundaries have to be crossed. So what are the boundaries we are talking about? If my system, if my final application has to run in 2 data centers or 4 data centers, the architecture will change, because I have to then figure out where data will be kept in each data center, or will I centralize all data in one data center. So boundaries are of various types. One example is the boundaries between data centers. Then if my final application has to run on multiple systems within the same data center, the architecture will change. Are these systems similar or dissimilar? For instance, if I have my transaction data on a Postgres database running on Linux, and I have my customer database in a Microsoft SQL server running on a Windows server, they are 2 different, very dissimilar data stores. They don't connect naturally to each other. So if I have these constraints, wherever there are boundaries to be crossed, boundaries to be bridged, they will have an impact on the architecture. So these are some basic points on architecture. We've sort of taken a quick look at a quick survey of the things which impact architecture. We'll go into details later. There are many episodes left. So I now come to something even more basic. We did a basic question, why do we need to do architecture? Now I'm getting even deeper, absolutely at the ABC level. What is architecture? What is the architecture of a software application? I'm asking this question not because I love to play a textbook or I love to act like a boring professor in a college class. I'm asking this question because I see non-clarity all around me. People just blend and merge different concepts which are applicable at different levels of the stack, left, right and center. So I thought it would be a good exercise for me to try to get into the basics and look at what my answer is to this question. What is architecture? Now, when I look at architecture of a software application, I define it partly by what it is and partly by what it is not. So architecture is not the code of the application. No, the software code that you write is not architecture. Architecture can impact the way you write the code, but that's different. Architecture is not the code. It is not the design of your web service calls at an individual level. It is not the design of, whether your table will have 55 columns or 57 columns. Those decisions are not part of architecture. It is not the functional features. It is not, for instance, issues like whether I will have a voucher entry permitted to everybody, or whether I will have a voucher entry which will be done by an accounts clerk and then will have to be checked and approved by a manager. These are functional decisions. Do I have a requirement for an approval of a voucher entry? Is a functional decision. This is not an architecture decision. So what is architecture? It's basically 2 things. The components which make up the final running system and the data flow among them. The components and the data flow. I'll give you an example diagrammatically. Now this next slide. Okay, this is not architecture. Look at this slide. What this slide is depicting is one box, the first box on the left hand side is order entry. So after order entry, what happens? The order goes to a manager for approval and the manager approves. Assuming the manager is in a good mood and approves the order, then the approved order goes to the next 2 functional areas. One area is it goes to accounts. So the arrow going up towards the right, it goes to accounts, and the accounts department enters that order into an accounting system. The other direction in which the order flows is it goes to the vendor, because I'm placing an order on somebody, right? So that somebody is the vendor who will supply me the goods. So order entry followed by order approval, followed by going to accounts and going to the vendor. This is a picture which shows how a business operation is performed, how something is done from one step to the next. This is not architecture. This is a flow of tasks. It talks about business operations. This is what we call functional specifications. This is the functional flow. This is extremely critical. This is what software is made of, but this is not architecture. So what is architecture? Look at this diagram now. This diagram has an order processing server and a financial accounting server. So it depicts two servers, an FA is for financial accounts, FA server and an order processing server. The order processing server is where orders go in, and from that order processing server maybe some data will flow to the financial account server. So there is a data flow being described. Maybe, I'm just showing you a diagram. If I write text together to go with the diagram, I will probably describe the data flow. So there is an order processing server, order processing database, financial accounting server with its own database. So there are two separate databases here, which clearly indicates that the entire data of the system is not in one place, it's in two databases, at least two databases, and we have a message bus, an enterprise service bus, which connects these two components in the system and allows messages to flow from one to the other. So this is a diagram of components and data flow. This is architecture. So the previous slide is functional, this slide depicts architecture. Now what's very interesting is we were describing the same scenario but from two different points of view. So there is an architecture point of view. These things are mixed up so often. As I said, if I had $1 for every time these two things are confused, well, I'm not that rich. So I guess the people who are confused about these things don't talk to me much. Or maybe they don't give me the dollars. So there is an architecture perspective and a functional perspective to look at the same software application. So architecture deals with components and flow of data. It does not deal with the operations which the user will perform on the system. That is functional. It does not deal with the contents of messages, the database schema. It does not deal with users and user profile. It does not answer questions like, for instance, the manager will be approving the order and then the accounts clerk will be entering the order. That is functional. That's not architecture. So I will give you two sentences now to show you the two different perspectives. Look at this sentence. The MIS reports are being generated by BIRT. BIRT is a reporting engine. BIRT running on the reporting server and are sent to the query system over the enterprise service bus. So the sentence talks about certain types of reports being generated using a certain software component running on server X and being transferred from server X to server Y using a connectivity component, which is the ESB. Now, when you talk about these things in this way, this is architecture. Now let's look at the next two sentences. The next paragraph describes the same sort of thing happening but completely from the functional perspective. Now, what does it say? The MIS reports are generated from the sales data and are viewed by the regional managers once a week. They show sales grouped by region and by product category. This is functional. This is not architecture at all. This is what software developers do when they write code. They need to know what the MIS reports will contain, who will view the MIS reports, and will the data be grouped by product category or by price or by region or by location or whatever. That's the stuff of the functional features of the software. So if you can see the colors, the blue sentence is the architecture perspective and the red-brown sentence at the bottom is the functional perspective. So this is, I hope I have tried to explain, this is the architecture of a business application. What is architecture itself is an area of confusion. Architecture is the other side of a business application other than functional. So we come to the end of this episode. In the next episode, we will be looking at all sorts of other interesting things. We will be looking at the tools and patterns by which an architect does architecture. You do architecture. So we'll talk about how we do architecture in the next episode and go on and on from there to other things. So thank you for watching and see you in the next episode.